This is College Algebra, Chapter 3, Section 4, where we're going to talk about zeros of polynomials. And zeros of polynomials, depending on the degree of the polynomial, there can be many of them. So we want to make sure we know how to find out what our options are, and then to test and see if any of those options are actually zeros. And the first tool that we use in order to make that determination or that list is the rational zero theorem. And what the rational zero theorem does is it helps us determine a list of possible rational zeros. Now remember what a rational number is. It's any number that can be expressed as a fraction. And a rational function is similar. It also involves fractions, where you have an expression in the numerator and denominator and the variables in the denominator. Anyway, when you think rational, be thinking fractional. And the number 3 is considered a rational number because it can be expressed as a fraction, 3 over 1. The decimal 0.25 is a rational number because it can be expressed as a fraction 1/4. 0.25 or 1/4 is also an example of a terminating decimal. It's a decimal that does not go on forever, as opposed to like 2/9. 2 over 9 is obviously a rational number because it's a fraction, but the decimal equivalent is 0.22222 repeating forever. So that is a non-terminating decimal, but it is a repeating decimal. So if your decimal is terminating, the number can be expressed as a fraction. That makes it a rational number. If your decimal is non-terminating, but it is repeating, it can also be expressed as a fraction, making it a rational number. Now, a number like pi or the square root of 2 or e, none of those numbers can be expressed as a fraction. They're decimals that go on forever, but they never repeat. So they are considered irrational numbers as opposed to rational numbers. So the rational zero theorem is going to help us find zeros of a function or potential zeros of a function, and the numbers that are returned to us by the rational zero theorem will be rational numbers. And now you've been reminded what rational numbers are. We use the rational zero theorem when we're looking at a polynomial like this one. And what we do, so I'm going to use this example in conjunction with the information that's in this blue box here. And what this information for the rational zero theorem tells us is that if we take all of the possible factors of p and divide by all the possible factors of q, and we reduce all those fractions into their lowest terms, then we're going to have a list of the possible rational zeros. Now, what are p and q? P consists of all of the factors of the constant term a sub 0, so that's the number that comes at the end. In example number 7, that's 15. And q represents all the factors of the leading coefficient, a sub n, which in example number 7 is this leading coefficient of 2 out here. So again, p over q we need all the possible factors of the constant value. 15 is divisible by 1 and 3 and 5 and 15. And all the factors of the leading coefficient q. 2 is divisible by 1 and divisible by 2. So we're going to use this list in order to make a list of rational numbers. So I'm going to take each of the numbers, each of the p values, and divide them by each of the q values. So we have 1 over 1 and 1 over 2. And then I'll take the 3 from the numerator, so to speak. We'll take the 3 divided by 1 and the 3 divided by 2. and the 5 divided by 1, and the 5 divided by 2. Thankfully, this is almost over. 15 over 1, 15 over 2. And then let's clean this list up a little bit. Certainly 1 over 1 is equal to 1. We have 1/2, 3, 3/2, 5, 5/2, 15, and 15/2. It does happen sometimes that once you make this list, that you'll have duplicates. And if you end up with any duplicates, you should leave those out of your final answer. Now, we also need to consider, and let's see if it's articulated in this box here. It doesn't say it explicitly. However, each of these rational zeros, I've listed all positive numbers here. We need to consider their negatives also. So if you're typing this list into an online homework assignment, type in all these numbers separated by commas, and then type them all in again with negative signs in front of them, separated by commas. I'm just going to put a plus or minus in front of each one of these. I recommend you do that too, so that you're aware from looking at your own notes that there's the possibility that each one of those numbers could be positive or negative. And that's it. Given this particular polynomial function, this is the list of all of the possible rational zeros. Let's remind ourselves of what is a zero. A zero is an x value such that when we plug it into our function, we get out a y value of 0. So maybe f of 1 is equal to 0. Maybe f of -3/2 is equal to 0. We're not sure. All we've done so far is generate a list of possible rational zeros. In this equation, we're asked to list all of the possible rational zeros and then use synthetic division to test the possible rational roots and find an actual root, and use the quotient from the previous step to find the remaining roots. Oh my gosh, and solve the equation. This might take a minute. Thankfully, our numbers are a little bit smaller for our p's and q's, so let's make the list of possible rational zeros. I've got p over q. That's all the factors of 4, which is 1, 2, and 4. And we'll include the negatives again in a moment. And we're going to be dividing by all the factors of 2, which is the leading coefficient. So that's a 1 and a 2. That helps us generate this list. 1 over 1, 1 over 2. 2 over 1, 2 over 2. 4 over 1, and 4 over 2. And then let's clean up each one of those fractions and see what we have. This is a 1 and a 1/2 and a 2 and a 1 and a 4 and a 2. So I'm seeing some duplicates here. The 2 is appearing twice and the 1 is appearing twice. So I'm going to leave those out and I'll have my final list of possible rational zeros. Let's put a plus or minus in front of the 1, plus or minus 1/2, plus or minus 2, and plus or minus 4. So there's the possibility that one of these is actually a 0 of our equation. And I did a little bit of preliminary work before I started making this video to figure out which one of these 8 possible zeros is actually a rational zero of the function. And I found one. I found it by graphing my function. I know it's tough to see. Maybe you can't see it at all. See, it's blurry when it's up here, but when you come back here, it's in focus, but then it's too far away to actually see what's on the screen. But I promise you, if you take this function and you graph it, you should be able to estimate, or if you go into Desmos, it's really easy to just drag your cursor over where it's touching the x-axis, and you can see what some of the zeros are. Right, so let's test and see if maybe positive 1/2 is a 0 of this function. We're going to test to see if 0 we're going to test to see, that says C, if 1/2 is a 0 by doing synthetic division as the instructions recommended. The other way that you could find out if it's a 0 is by plugging it into the function and seeing if you get an output value of 0. The reason why it's going to be helpful for us to do the synthetic division is because if it is indeed a 0, then we will have done some initial work which will be helpful. We'll have already done the division, and I will show you why that's to our advantage. If you're a little rusty on your synthetic division, depending on when you're getting into this video, feel free to look back through my channel if you'd like. I do definitely have a video about doing long division and synthetic division. So this is the setup for synthetic division. I put the 0 up in the little box. I listed my coefficients next to the box, and I always take that first leading coefficient of 2, or whatever it happens to be. Here it's 2. I bring it down below the line, and then I start this repetitive process. I take the number from the box, I multiply it by the number below the line, so that's 1/2 times 2, which gives me a 1. And then I add vertically, -5 plus 1 makes -4. And then I repeat, 1/2 from the box times -4 below the line equals -2. And then I add vertically, which gives me -8. And then I repeat the number from the box, 1/2 times the number below the line. 1/2 times -8 makes -4. I add vertically, I get 0. 0 is my remainder. A remainder of 0 tells me that the division did happen evenly, so to speak. And let me show you what the implications of that are. So originally I was taking my third degree polynomial, 2x to the third power, and I'm dividing it by, what am I really dividing it by? The 0 was 1/2. So what am I actually dividing by? I'm taking my original polynomial and dividing it by x minus 1/2. So x to the third divided by x to the first is equal to x squared, which means that this 2 represents 2x squared, and the -4 is how many x's I have, and the -8 is my constant value. Remember that when we take 6 and we divide it by 3 and we get an answer of 2, 3 is called the divisor, 2 is the quotient, and 6 is the dividend. The quotient times the divisor equals the dividend. The same thing is true when we do polynomial division. This is the quotient. It's the result of our division. If we multiply by the divisor, we would get our original function, the dividend, which if you want to write it in place of f of x, it's this thing up at the top, 2x to the third minus 5x squared minus 6x plus 4. Why am I happy about this? Well, let's read these really long instructions again. List all the possible rational roots. Okay, let's circle those because we did that. This is part of our final answer. Use synthetic division to test the possible rational roots and find an actual root. We got lucky and we tested 1/2 as a 0, which allowed us to find an actual root. So that is positive 1/2. And then we use the quotient from the synthetic division process to find the remaining roots. So in order to find the remaining roots, or you could say the remaining zeros, what I'm going to do is I'm going to factor, if possible, I'm going to factor my quotient. Let's see if we can do that. Let me see if I can do it. 2 and 4, and it's not going to be good. The only thing that I can do, I can tell, is I can factor a 2 out of it. So let me do that. 2 times x squared minus 2x minus 4, still times x minus 1/2. Now this is equal to our function. However, notice that our original function is set equal to 0. So this 0 right here, I'm going to replace my f of x with a 0. And we're trying to, at the very top of the screen there, you see our last set of instructions says solve the equation. In other words, we're trying to find the x values that make this equation equal to 0. Certainly an x value of 1/2 is going to work. We already know that that's one of our zeros because we did the synthetic division and got a remainder of 0. So we knew that the 1/2 was going to be a 0. How do I find my other zeros? Well, normally, in a situation like this, you would take this factor and set them each equal to 0. X squared minus 2x minus 4 equals 0. X minus 1/2 equals 0. And then we'd add 1/2 to both sides here, and we would get x equals 1/2. And that's one of our zeros. That's great. Now I have to find the zeros using this other little equation, x squared minus 2x minus 4 equals 0. The problem is it's not factorable, which means you're either going to have to complete the square or use the quadratic formula in order to determine the zeros that come out of that factor. I'll leave it up to you. I'm going to complete the square. You do whatever you want, and let's see if we get the same answer. So I'm going to add 4 to both sides. And then I'm going to take the -2. I'm going to divide it by 2, which is -1. And then I'm going to square that, which gives me a +1. And then I'm going to add 1 to both sides of my equation. So I'm going to put in a +1 in a different color there. And if I add 1 to the left-hand side, I have to add 1 to the right-hand side. Come here. Come on. So noisy. It's one of my fur babies. She'll be joining us up here momentarily, I'm sure. Now on the left-hand side of this equation, we can factor. It turns into x minus 1 times x minus 1, which I will write as x minus 1 squared. And the right-hand side adds to 5. And then we can solve this equation by taking the square root of both sides. Sophie, don't go in there. Just come say a quick hello. Say hello. Yes, good girl. Why don't you come up here and just sit for a minute? Good. Let's take the square root of both sides. Now we have x minus 1 equals plus or minus, just stay up here. Just stay there. Plus or minus the square root of 5. And then if we add 1 to both sides, we find that x is equal to 1 plus or minus the square root of 5. These are our other two roots, or our other two zeros. Now, if the 5 had turned out to be a negative number, then we would have two imaginary or complex solutions in the form of a plus bi and a minus bi. In this case, these are just irrational solutions. They're not rational because there's no way that we can express 1 plus the square root of 5 as a fraction. So that's why that wasn't in our list of possible rational zeros. However, those are our other two zeros. Should we have been able to anticipate that there were going to be 3 zeros? The answer is yes. Our original equation is a third-degree polynomial. Notice that it says 2x to the third. So it was probable even that we were going to have, well, it was certain that we were going to have 3 zeros. We didn't know if they were all going to be real zeros, however. All right, so those are our solutions. I think we've answered all of our questions that were part of that question. Properties of polynomial equations. So what this is talking about is that possibility that some of our solutions could end up being complex. And we see the word complex right in here. They could be complex imaginary numbers a plus bi. if a plus bi is one of your roots, then it's necessarily true that a minus bi is going to be one of your roots. So I said that backwards, but just read through number 2. If a plus bi is a root, then its complex conjugate, a minus b is I, is also going to be a root. And we're seeing some of that up here. A plus the square root of 5 is our b value, except it doesn't involve the I. So this is not a complex number. It's a rational, or it's an irrational number, but 1 minus the square root of 5 is also a solution. Those two numbers, I would still call those conjugates of each other. 1 plus root 5 and 1 minus root 5. The fundamental theorem of algebra tells us that if we have an nth degree polynomial, if the polynomial of degree n, where n is greater than 1, then the equation where you take f of x and set it equal to 0 will have at least one complex root. That's interesting. That's interesting to me. I would like to know what their definition of a complex root is. When I think of a complex number, I think a plus bi. You can use a plus bi like that format, a plus bi. You could use that to describe a real number. You would like, is it possible that a plus bi could represent the number 7? Sure, it would just be 7 plus 0i. So if what they're trying to tell us in the fundamental theorem of algebra is that if we take a polynomial and we set it equal to 0, it's going to have at least one root, yeah, absolutely, totally agree. Let's check out the linear factorization theorem. All this tells us is that, and I'd like to even just go ahead and skip down to here, in words, an nth degree polynomial can be expressed as the product of a non-zero constant and n linear factors. That's true. We're looking at an nth degree polynomial. We can express it as the product of a non-zero constant. Here it's described as a sub n. Sometimes a sub n is a 1, and you don't actually see it, but it's there. And then here are your n factors. We're going to work with one of those next. We're going to engineer one, actually. And it's going to give us this problem gives us the opportunity to work with complex zeros. So the instructions are asking us to find an nth degree polynomial. The problem goes on to tell us that n is equal to 3, so it's a third degree polynomial, with real coefficients satisfying these conditions. So n is 3, so it's a third degree polynomial. 4 and 2i are zeros. And for some reason, they're telling us that f of negative 1 is equal to 50. That's the very last thing that we interact with of the given information, is that f of negative 1 is equal to negative 50. Now, what is our polynomial going to look like? Let's call it f of x, and it has the potential to equal some leading coefficient a times these 3 linear factors. Let's have it be x minus b and x minus c and x minus d. Okay, so what of these blanks can we fill in? Well, I definitely don't know what a is yet, so I'm going to leave that there. And x minus 4 is the first of those unknown constants that I'm going to fill in. How do I know that it's a 4? Because, as you might be guessing, there's a 4 right here. Well, how do I know to put it in as x minus 4? Maybe it should have gone in as x plus 4. Remember that these values up here, 4 and 2i, are zeros, which means that if we plug them into our function, they're supposed to cause our function to end up equaling 0. Well, for sure, if I put in a 4 right there, 4 minus 4 is 0, and then I do all my multiplication with a 0 built in, and the answer is going to be 0. So that's how I knew to put an x minus 4. If we follow that logic, we should be able to put x minus 2i, because positive 2i is another 0, so positive 2i minus the 2i that I just put in there causes it to be a 0. And what about this last one? Remember that we talked about complex conjugates a moment ago. If a plus bi is a 0, then a minus bi will also be a 0. What this problem tells us is that 0 plus 2i is a 0 of our polynomial, which necessarily 100% certainly means that 0 minus 2i is a 0 of this function that we're trying to design. So I'm going to come over here and I'm going to put minus negative 2i, just to really drive home the point that we are putting in a negative 2i instead of a positive 2i, and that's the conjugate. Now what do? Now we can start multiplying. We're going to do some foiling. I'm going to leave the a, and I'm going to leave the x minus 4, and I'm going to FOIL these two conjugates. I'm going to do those first every time. If I have complex conjugates, these are only moderately complex conjugates, but if I have conjugates, I'm going to FOIL those two first. So I've got x times x makes x squared. Realize, please, that this is really x plus 2i. So we can write plus 2ix. So that's the firsts and the outers, and then the inner gives me a minus 2ix, and then the lasts, that's a negative 2i times a positive 2i. So negative 2 times positive 2 makes negative 4, and I times I makes I squared. Now you should know that the definition of I squared says that I squared equals negative 1. So this really says negative 4 times negative 1. So it's going to turn into a positive 4 the next time I write this thing out. Let's do that. Also, the O and the I terms canceled out. Anytime that you multiply conjugates, your O and your I terms will cancel. Anytime you FOIL conjugates, the O and the I terms will cancel. Great, now I can FOIL again. We'll FOIL these two factors. That's x to the third. I'm going to FOIL out of order here. That was the firsts. Now I'm going to do the inners in order to get minus 4x squared. And then I'm going to do the lasts. No, I'm going to do the outsides, giving me a positive 4x. And then I'll do the lasts to get minus 16. That way my exponents are already in descending order, to the third, to the second, to the first, and then my constant value. This is getting pretty close to looking like a polynomial. We've used all of the given information. The only other thing I could do is distribute multiplication by a, which I'm not going to just yet. Now I'm going to use the last piece of given information, that f of negative 1 is equal to negative 50. So I'm going to put, how should I write that? How about negative 1, sorry, f of negative 1 equals a times negative 1 to the third minus 4 times negative 1 squared plus 4 times negative 1 minus 16. And remember, f of negative 1 equals negative 50. So I'm going to go ahead and put equals negative 50 over there. Now let's figure out what all this stuff in parentheses equals. Negative 1 to the third is negative 1. Minus 4 times 1, so that's still a minus 4. Plus 4 times negative 1, that turns that into a minus 4. This is still a minus 16, and it still equals negative 50. So this is equal to negative 5. And this is equal to negative 20, which means it's all equal to negative 25. So a times negative 25 equals negative 50. We can divide both sides by negative 25 now to get our a value finally. We've got an a value of 2. I'm going to take this 2 and I'm going to plug it back into here. Now don't draw that line that I just drew. Let's do something a little bit more graceful. Let's put a star next to our almost completed polynomial there that we were just missing the a value. Let's down here where it says a equals 2, let's say combine with star, or you could say plug into star. But what that's going to let us do is write our second to last line for this problem. F of x is equal to 2 times x to the third minus 4x squared plus 4x minus 16. That's from the starred equation with our a value of 2 plugged in. Now I'm going to distribute, and that's going to be my final answer. That's a time-consuming problem. But you know how to do these things. You know how to FOIL. You know how to combine like terms. You know how to FOIL. You know how to plug numbers in. You can do arithmetic. You can solve for a. You can plug it back in. You can distribute. The most challenging part of this problem is really getting it started, knowing what kind of a format or a sort of a skeleton you're supposed to be plugging this stuff into. Setting this up and then plugging in those given zeros, knowing to plug them in the way that we did, and then also being aware of the fact that that conjugate came into play. We were given a 0 of 2i. We had to also use negative 2i. And when I say we had to, I mean we had to. If 2i is a 0, negative 2i definitely will be a 0. If 3 plus 7i had been a 0, then 3 minus 7i would have been a 0. From there, once you've got those zeros plugged in, maybe doing this foiling process is a little bit tricky because it involves the imaginary number I would definitely do some practice with that if I were you. How am I supposed to find practice problems like that? Well, you could design your own. I'll tell you how to design your own. If you have x squared plus some other number squared, like maybe this ends up equaling x squared plus 25, okay? X squared plus 25 is factorable if you're using imaginary numbers. It's equal to x minus 5i times x plus 5i. So what you should do is you should try to FOIL this and see if it takes you back to this. All right, just do that a couple of times and make sure you get more familiar or comfortable with the I squared equaling -1, and it changes the sign on that last term. Otherwise, there's no sense practicing the rest of it. Go through and make some labels on this process and kind of group the different sections of the process. Here we were just plugging in given information. This was all about foiling and combining like terms. We foiled twice, as a matter of fact. Then this was its own stage, using the given information, in this case that f of -1 was equal to 50. So that's its own stage in order to get your a value. And then all you have to do is plug the a value back into that start equation. Well, the way that I've outlined this, it's only a 3-step process. Go from the macro to the micro, okay? Get a feel for the big picture of the process and then start thinking about what the smaller steps are. Practice, practice, practice is going to help you with that process. Descartes' rule of signs, you might have heard me mention in a previous video that Descartes designed or invented the XY coordinate plane. It's called the Cartesian coordinate plane, named after René Descartes. Cartesian coordinate plane. Descartes was not only a mathematician but a philosopher. We're going to focus on his mathematical stuff. I was just making another video for a different course where there was this crazy looking curve that he had named, and I don't even remember exactly what it looked like, something like this. And we were talking about derivatives, and it was madness. Descartes must have had a lot of time on his hands. What Descartes' rule of signs helps us do is determine the number of real zeros that a polynomial can have. How do we make that determination? How does this Descartes rule of signs thing work? What you do is you look at the original polynomial. So let's say that this is our given polynomial. It's in descending order of exponents. So you see the largest exponent comes first, and then smaller, 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 all the way down to the constant value. When you've got your polynomial laid out like that, the next thing that you do is you start looking for sign changes. So our first term here has a leading coefficient of +3, and our second term has a coefficient of -2. So going from +3 to -2 constitutes a sign change. From negative to negative does not constitute a sign change. However, going from a negative coefficient here to a positive coefficient here does indicate a sign change. Here's positive to positive, so we don't count that one. But going from positive on the x to a -3 as our constant, that does still count as a sign change. So we found 3 sign changes in our given polynomial. So what does that tell us? Just reading from this, the number of positive real zeros of our function is either the same as the number of sign changes or less than the number of sign changes by a positive even integer. Somebody got paid to write that. And then someone else read it and thought, that's crystal clear. Every college algebra student on the planet will be able to understand that. No. What it really means is, or what they're trying to say is, this polynomial at the top of the screen, we went through, we counted sign changes. So how many positive real zeros is that function going to have? It's going to have either 3 or 1. How did you change a 3 into a 1? I subtracted 2. Why did I subtract 2? Because we had the possibility of having 3 real zeros. If it turns out that one of these real zeros isn't a real zero, if it turns out to be a complex zero, an imaginary zero, then can we just take away this one? No, we can't, because complex zeros always occur in pairs. So we have to take away another 0, because if the real zeros leave and become imaginary zeros, they're going to leave in pairs. I'm going to choose these two. Okay, then we would only end up having one real zero. Real versus imaginary, okay? So that's what they're talking about with a positive even integer. Just keep taking away 2 until you get down to 1 or 0. The number of negative real zeros, okay? So be careful here. Well, we just determined the above problem might have 3 or 1 positive real zeros. How do we figure out how many possible negative real zeros that polynomial is going to have? We take negative x and we plug it into our function. And then we count again, looking for the number of sign changes. Let's just keep working with this function up here. 3x to the 7, that's not the same as this one. That would have been clever. Let's figure out what f of negative x is. F of negative x equals, if I take a negative value and I plug it in here and I raise it to an odd power, it's going to change the sign of that term. So this will become negative 3x to the 7. Plugging a negative x in, raising it to an odd power, is going to change the sign on that term too. So this is going to become positive 2x to the 5. Plugging a negative value in and raising it to an even power is not going to change the sign. Why not? Because, so I've got x to the 4th. Let's plug in negative x. What's negative x times negative x? Positive x squared. And what about here? What's negative x times negative x? Positive x squared. And what's positive x squared times positive x squared? Positive x to the 4th. So this becomes positive x to the 4th, which does not impact that negative sign. With positive x to the 4th, if I had to introduce another multiple of negative x, then the whole thing would have become negative x to the 5. Double negative, it would have become positive. Moral of the story is our third term is going to stay negative x to the 4th. Can I write and talk at the same time? It's looking like no. Negative x to the 4th, there we go. Another even exponent, so that sign's not going to change. So we have positive 7x squared. Odd exponent, that's an x to the 1st technically, so that becomes minus x minus 3. Great, let's look for sign changes. Give me red. There we go. Negative to positive, that's one sign change. Positive to negative, sign change. Negative to positive, sign change. Positive to negative, sign change. Negative to negative, not a sign change. Let that go. So how many sign changes do we have? 4. That means there will be 4 or 2 or 0 possible. No. It's 4 or 2 or 0 possible. What's happening? Now what's happening? Hold still. Negative real zeros. You think that's irritating. Just wait till I teach you how he figured this out. I'm just kidding, I'm not going to teach you that. You'd quit immediately. I would quit immediately if I had to describe to you how it is that he came up with that. So that's Descartes' rule of signs. And that is the end of our notes for this section. I have no idea what's coming next, so just click on that square. Where is it? I think it's going to be, should I point with the other hand? Is that helpful? I think maybe it's going to be down there. Click on something that's over here. That'll take you to the next video. Let's see what's happening in our next section. Thanks for being with me for this one.